We start with special relativity, 3 variables, energy, momentum, and rest mass. C is a constant. Notice the Pythagorean relationship. E squared is equal to p squared plus m squared. P is a vector, so we can display it in the normal means with Cartesian axes. E and m are scalars. We represent them as concentric spheres. And there, both E and m are co-planar with P. We can treat E and m as vectors in this construction. And because of Pythagoras' triangle, m is perpendicular to P. So here we have a display in 5 dimensions. It's cylindrically symmetric. We need to go on to display other variables. But first of all, we want to know what is the band structure and the band gap. We start with extrema. As p goes to 0, the solution is a horizontal tangent. And as p gets very large, vertical tangents on m0. The solutions are shown on the right with a band gap of 2m, and you can think of this as the band gap between the electron and the positron. So we have a display of 5 dimensions for special relativity. There are other dimensions that we listed in the legend. To view those, we will move to dispersion dynamics using Planck's law and the de Broglie relationship, and find omega squared is k squared plus m squared in natural units. And 2 preliminaries, the quantum uncertainty. Here's a quantum derived from Maxwell's equations: electric vector vertically, magnetic vector horizontally, 2 velocities, a group velocity and a phase velocity. And in the photon they're equal, but in massive particles the group velocity is smaller than the phase velocity. The uncertainty is the full width 1 over e times maximum, and it can be quickly derived from this equation: dt is 2 sigma over omega. And after Fourier transform, d omega is 4 omega over sigma. The dual uncertainty d2 by d omega is equal to 8. This is 16 times larger than Heisenberg's limit, whatever that is. To move on, we need to take the derivative of relativity, and we find omega over k multiplied by the derivative d omega by dk is equal to c squared, which in natural units is 1. What is omega over k? That's the same as lambda nu. That's the phase velocity. And what's d omega by dk? That turns out to be the beat velocity for a normal distribution. And so we have that the product of the phase velocity and the group velocity is equal to 1 in normal units, in natural units. Here they are. There's the group velocity in Newtonian physics and in relativity physics, where the velocity goes to c, as Einstein taught. The rest mass is a constant, but in relativity the mass is energy dependent, and the phase velocity is the inverse of the group velocity. Again, if you need to read this, press pause. This gives the derivation of the phase velocity and the group velocity from classical to relativity physics. And so here we show how to display the group velocity and phase velocity, where we've moved the Cartesian axes to the end of P and compared the velocities with the velocity of light in dotted lines. On the right is Minkowski space with time and the x direction, the direction of propagation, shown in normal Cartesian axes. And we can extend the same ideas to 48 dimensions listed here. All very easy to describe, and the gaps are easily simulated. The planar solution has Cartesian spatial projections of vectors, spherical scalars, co-planar constraints, cylindrical symmetry, and many other dimensions.